The difference of squares is one of the easiest factoring patterns to recognize because it only consists of usually two terms with a minus sign between them. An example of a problem that can be simplified, or an expression that can be simplified using the difference of squares, is something like 64x squared minus 121y to the fourth. In a difference of squares situation, we are looking for a square minus another square, and that's exactly what we have here. 64x to the second can be thought of instead as 8x times 8x, and 121y to the fourth can be thought of as 11y squared times 11y squared. Because I am able to do that split, the difference of squares tells me that I can factor this fairly quickly. I'm going to start both of the binomials with 8x and finish both of the binomials with 11y squared. But in order to make this a true difference of squares, we need a minus sign in one of the binomials and a plus sign in the other. If you're thinking about foiling and multiplying out these binomials, and seeing that you get back to where you started, 8x times 8x is 64x squared. 8x times 11y squared is 88xy squared. 11y squared times 11x is minus 88xy squared. And 11y squared times 11y squared is 121y to the fourth. And we can see that these two terms are opposites of one another, therefore they sum to 0, and we're left with our original binomial. In some cases, you have to be a little careful applying the difference of squares, especially in those situations where it might look like an obvious candidate. An example is 100 minus 400 z to the sixth. This looks like a classic candidate for the difference of squares. 100 is just 10 times 10. 400z to the sixth is 20z to the third and 20z to the third. And the thinking would go, following our last example, that we could simply break our original binomial into its factored form. But an observant eye will notice that in here and in here are a common factor. Looking back at the original binomial, we should have clocked that in the original binomial, there was a common factor of 4. So while this is not wrong as a, quote, factored version of our original binomial, it is not the most factored or completely factored version. In order to do that, we're going to have to start by removing our common factor of 4. We remove our common factor of 4, and we're left with a binomial of 25 minus 100z to the sixth. Fortunately for us, that is also a difference of squares, so we can continue our factoring one more line and use both of the squares in that binomial to create another difference of squares. Could we have taken 2 out of this parentheses and 2 out of that parentheses and created our common factor of 4? Sure, you could do that. But if we want to stay with the mindset of greatest common factor first, even in those situations where it looks like the difference of squares is an easy example to use, or an easy process to use, we want to still do that check for, does this fall into the category of something with a greatest common factor? Lastly, we want to look at an example of the difference of squares that doesn't exactly follow what we might think. And that example is something that looks like this. Now you can clearly see that this is the difference of 2 squares. Here's a square, and there's the minus sign. This is clearly a difference of 2 squares, but obviously each one of those squares is its own polynomial. The first one is squaring 3x minus 2. The second one is squaring 6y minus 2. So we can apply the difference of squares to this being very careful with our simplifying, being very careful with our positioning inside of the parentheses. So in our first parentheses, we're actually going to use a bracket because we're going to need multiple terms inside of here. So here's going to be our difference of squares. We're going to have a minus sign in one of them and a plus sign in the other. And we are taking the square root of both of these parts of the polynomial. But fortunately for us, that's just 3x minus 2 and 6y minus 2 and 3x minus 2 and 6y minus 2. We took our original difference of squares and we split it into the positive sum and the negative sum of each square root. Now, this is technically not incorrect. You could write this answer and say, I have factored my original expression. But one could make the argument that this is not any better looking than that larger expression at the top. We want to go a little bit farther. So continuing with our simplifying, we have 3x minus 2 plus 6y minus 2 coming out of the first parentheses. And then in the second parentheses, we have 3x minus 2 minus 6y plus 2 out of the second one. Simplifying the first one a little bit farther, we have 3x plus 6y minus 4. Whoops. And in our second parentheses, we see the negative 2 and the positive 2 sum to 0. So in our second parentheses, we have 3x minus 6y, and again with the bracket. So this is what we would consider to be the factored version of our original polynomial. Now, some of you, the observant, might notice that, again, this is not completely factored. So we could throw in one more line. We're pleased to have used the difference of squares, but we could throw in one more line where we factor the 3 out of that parentheses, and then we follow that with that larger parentheses that came out of the first use in the difference of squares. So if we want to factor it completely, I suppose we would have to give this answer to make sure that we have each individual term as factored as it possibly could be. But all of these examples came from just an application of the difference of squares. One square minus another square being able to be factored with their individual square roots.